All right, so we continue with our next speaker for this morning, which is after Pander Maat. We're going to talk about the Eilenberg-Watts theorem and Morita theory.
Yeah. Hi everyone, really cool to be here with all of you, and thank you so much for organising. I'm going to be presenting some results from my ongoing PhD thesis, which is supervised by Aoife de Lambrojo, who's at the University of Lille, and Birang Nuhi, who's at the University of London. Really quick bit of admin up top is that I was told at the school dinner last Wednesday that a PhD thesis has just come out a month ago, which also contains some of the results in this presentation. I guess that goes to show, make sure you go to the dinner on Thursday, because you never know what you're going to find out. Anyway, I've indicated in this presentation, I've read the person's thesis, I've indicated in this presentation where I think there's an overlap. His name is Matthew Ferrier. But yeah, that's that. So I'm going to be telling you guys about the Eilenberg-Watts theorem and about Morita theory for C-star category. So I guess most people probably know what an Eilenberg-Watts theorem is. It's a theorem that says that that characterizes certain functors between module categories as being given by tensoring with certain bimodules. So I mean, this is quite an old result for rings, and I'm going to be talking about a similar result, but for Hilbert modules over C-star categories. Let's see if this works. Okay, so I should tell you what a C-star category is if you don't know. So C-star category is a not necessarily unital category. So you might call it a semi-category if you want to do. I'm just going to call them categories, which is enriched over Banach spaces, and it has an involution from A to its opposite, which also fixes objects and squares to the identity, such that you have a bunch of things that hold. So you have this sort of classical C-star identity, which says that the norm of A star A is the norm of A squared, and you have to ask, in addition, that A star A always has positive spectrum. So people who know about C-star algebras will know that in that case, the second thing here is a consequence of the first thing. But yeah, we have to require that extra in this situation. Okay, so I should give you some examples. I mean, there's sort of an annoying example, which is if you just have one object, this is just what a C-star algebra is. If you have a group with curly G, you can turn it into a C-star category, like a reduced group of C-star category, in the same way that we saw last week people turning groups into C-star algebras. This is, I believe, due to Ulrich Bunke, who's, oh, someone else. Okay, someone who's not in the front row right now did this. If you have a tensor product in your C-star category, you get what's called a C-star tensor category. These play a role in quantum group theory, and finally, another sort of annoying example, but important example, is if you have a complex linear subcategory, which is normal evolution closed, of the category of complex Hilbert spaces, that is another C-star category. Cool. Yes?
Ignorant question.
Yeah.
So what does it mean that the category is enriched over Banach space?
It means that all of its Hom sets are like complex linear vector spaces, which have a norm that make them complete vector spaces. Cool. Anything else? Let's carry on. So I promised you that I was going to tell you about what Hilbert modules over C-star categories are. So let's start with that. So a right Hilbert module over a small C-star category A, A and B are going to be names for like small C-star categories which have a set of objects. Is a contravariant functor from the category to complex linear vector spaces, such that you have, for every pair of objects in your category, you have one of these sesquilinear products. And these are going to satisfy a bunch of natural axioms, like, if you have like F over there, so F lives in E of X, you can act on it contrarially by a morphism that lands in X, and then you can take the product, or you can take the product and then compose with a morphism, and that's going to give you the same thing. E, comma E should always give you like a positive element. It should be this involution relation, and finally you want every component space of your Hilbert module to be complete in the metric that this gives you. So some examples, I don't have lots of super interesting examples for sake of time, but I mean, again, if your C-star category just has one object, this is just a Hilbert module over the endomorphism algebra of your object. So, I mean, these should all be familiar axioms from that situation. The other example, which is going to play an important role today, is that if you that the free Hilbert modules over C-star algebras are going to be replaced by representable modules. So for every object x of A, you have like a representable right Hilbert A module, which just gives you like the Hom set into X. And then if you have two morphisms into X and you want to take like an inner product, then you can flip one of them using the involution, and then you get a morphism that lands in there. Sure, I should have called this object Z, but you get the idea. So this is a strict generalization of just a free Hilbert C-star module over a C-star algebra. But there's one for every object. So what do these things form? I said I was going to tell you about module categories. So I've defined the objects. This is what the morphisms are. So bounded adjointable operators between right Hilbert A modules. Well, what are they? Well, they're natural transformations of functors, so they should behave well with respect to the A action. They have a bound, which is not just bounded over every object, but has like a uniform bound across all objects, because you want a bound on the set of operators. A norm on the set of operators. And finally, there's a dual operator which goes in the other direction, such that you have this natural like adjoint relationship. And again, keeping in mind here that E and F are allowed to live over different objects, but this should still be true. Cool. So there's a proposition by Michener from 2002. He defined what these Hilbert modules of C-star categories are, and he also proved that they themselves form yet another C-star category with the norm and the involution given exactly by the structure that I just explained. So a couple more facts I want you guys to take away about these Hilbert module categories. The first thing is that they have a sort of a topology of pointwise convergence along with a norm topology. So this should be familiar if you're thinking about operators over Hilbert spaces. I mean, you have a bunch of different topologies, and we say that a net T lambda of operators goes to T strongly if we have this pointwise convergence, as well as pointwise convergence of the adjoint for all possible indices. And the final thing that I'm going to tell you about, but not explain in lots of detail because it's very similar to the algebra case, is that just like in like we saw over C-star algebras last week, there's a very natural definition of what compact operators are between these Hilbert modules. I can write it down if anyone is like unsure, but it basically works the same way. You define a single rank operators, you take the finite sums of those, and then you close up under the norm. So that all sort of works out. Cool. Let's keep going. So I promise this barrage of definitions is going to end soon. I'm going to like do like a lemma or something. But so what is like a natural definition for like a bimodule? Well, it's just a functor from your first category, a covariant functor now, into the category of right Hilbert bimodules over the other one. So in other words, for every object of your first category, you have a module over the second one, which has inner products valued in the second one, but not necessarily in the first one. And you have a bounded adjointable left action from all morphisms of A. And a common requirement about these that we'll see today is that, like, usually you would like things to be like what I've called non-degenerate. So there's a bunch of different ways of defining that. You can say the images of the actions are dense in the thing, or you can say, like, if you have an approximate unit for an endomorphism algebra in your first category, then acting on the left on something in your bimodule should get you back in the limit, the original element. Okay. Some examples of bimodules. So every C-star category admits what I've called like the Yoneda bimodule. I mean, this is basically like an enriched Yoneda embedding where you take every object to its like representable Hilbert module, and then you act on the left by not pre but post composition by morphisms. So this is this takes every object to its representable module, and this is like, you should think of this as like an enriched Yoneda sort of functor. And the fact this is non-degenerate is actually sort of an interesting thing that you need to like work to show, but it is true. And then a much sort of higher level example of this is Michener, who had a very productive year in 2002, used right Hilbert bimodules of C-star categories to like prove some new things about KK theory. And this, yeah. So that's that. Okay. So let's move on. Oh, I just went back. I want to go forward. Yes. Okay, so how do we tensor a bimodule with a module? Remember I said we were going to do an Eilenberg-Watts theorem, so for that we need to explain how we tensor a bimodule with a module over just one of the categories. So again, I mean, this is basically like a strict generalization of how this works over C-star algebras. But you're just indexing over these little objects of your categories all the time. So, I mean, what you do is you take at every object Y, you sort of take the free module, the free module on these like symbols M cross E. You impose this naturality with respect to A. This is, if people have seen, like, ever heard of coends, like this is just a complex linear coend. Well, of course, if it's supposed to have like an inner product valued in B, then we should also explain what that is. So the way that you do that, again, very similar to the algebra case, is you have like two of these simple tensors. Well, these guys have like an inner product that is valued in A. So then using the bimodule, you can let that act on this thing in the bimodule, and then you take a product valued in B. And that's exactly what you want, because you want to end up with a right Hilbert B module. Okay, and then you need to complete in the resulting norm, otherwise. Okay, so first lemma of the day is that if you have a right Hilbert bimodule, an AB bimodule, which is non-degenerate, and then you just let the module M be like a representable A module, then this just returns like the value that your bimodule takes on the object X. How do you show that? Well, I mean, the proof isn't quite as short as I've made it out to be here, but basically, the way you construct this morphism is, remember, like something in here is just a morphism that lands in X. So then you let this act on something on this thing, and then you end up with something in like H in the tensor product. Sorry, yeah, in E of X, which is what you want because you have a covariant action here. You can work out quite easily that this is an isometry using the definition of the inner product. And then the non-degeneracy assumption basically tells you that this morphism has, this map has dense range, because non-degeneracy says, basically like elements like this are dense. So that works out. Cool. So what are some features of the tensor product? We want to be able to distinguish, we're going to like talk about tensor products as being functors, and then we want to be able to distinguish which like functors are given by tensor products. So first of all, the tensor product is functorial in quite an obvious way. So if you have a morphism of A modules, you can get a morphism on the tensor products with E by just letting like T act on like the left coordinate of simple tensors. This mapping has all sorts of obvious nice properties. I mean, it's complex linear, possesses identities, compositions, involution. So it's basically, it's a unital C-star functor from Hilb A to Hilb B. So it would be really nice if we could show that all functors like that are actually tensor product functors. But unfortunately, that's not possible. So we need to like impose something else. This goes back to work with David Bletchers from the 90s, where he was doing this with just C-star algebras. You would like your functor to be strongly continuous on bounded subsets, which is a bit of a mouthful, so I'm just going to call that property strong. So remember, Hilb A and Hilb B have these like strong topologies of pointwise convergence, and on bounded subsets of operators, we want this functor is going to be continuous also with respect to that, and not just with respect to the norm. What does the proof look like? Well, it's not too hard. I mean, you basically, you have a net in here that converges strongly to 0, and then you tensor it, you want to show that this net converges strongly to 0. You try on a simple tensor, and there's basically a type of Cauchy-Schwarz rule that lets you conclude that like this is bounded by this product, and by assumption, like these things go to 0. Then you extend that to finite sums, and then the fact that your net of operators is a bounded net of operators lets you extend that to arbitrary elements of this thing. Because remember, this is a closure. It's not just given by sums of simple tensors, but the fact that you have a bounded net means that you can do that. Okay, So this is the distinguishing property of tensor product functors. We want to show that every unital strong C star functor, which is just behaves well with respect to the involution, the composition, blah, 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 is actually given by a tensor product. And there's sort of an obvious candidate for like what the relevant bimodule should be here. So we have this functor from Hilb A to Hilb B. What should we do? Well, let's just precompose with this Yoneda bimodule, this enriched Yoneda embedding, which went from A into Hilb A, and then we'll get like a bimodule which goes from A to Hilb B. So how do we define like the map that does that? Well, it's sort of, if you've ever seen the proof of like an Eilenberg-Watts theorem, it's quite like a similarly defined map, except again you have to be a little bit careful because you're working over all these objects. You start with like one of these simple tensors, and then you notice there's a bounded operator from the representable module hx into M that just sends a morphism to like M dot A. So this is like a fairly obvious operator to define, and then the thing is, if you apply F to this operator, you get something which goes from like F of hx to F of M, which is where you want to be, because this Eilenberg-Watts map is going to land in F of M, right? This is the natural transformation which is going to exhibit that this functor is actually a tensor product. Does that make sense? I mean, that's a lot of symbols, but yeah. A fun additional fact about this is that actually transformations that look like this are always like compact operators, and there's like a Yoneda type lemma in my thesis which says that like a compact operator from hx to M is always given by one of these, so that there's like an isomorphism there between M of x and the compact operators from hx to M. Okay, cool. So we want to prove that this map is an isomorphism. That's going to prove our Eilenberg-Watts theorem. So how do we do that? Well, on representable modules, it's kind of obvious. I mean, this goes back to the thing that we were talking about before, where if you tensor with a representable module on the left, it just returns like whatever the bimodule was doing on that object. So yeah, I hope that makes sense. I mean, there's something to say here about the fact that F composed with HA is actually like a non-degenerate bimodule, but that follows from the strong continuity of this functor, so I'm not going to get into that. Okay, so because it's an additive functor, obviously that shows it's an isomorphism on like, you know, finite direct sums of these little representable modules. And even if you want to use a strong continuity as well, then you could actually show that this is like an isomorphism on arbitrary direct sums of free modules. So if we were in some sort of algebraic world, this would be almost like the end of our proof, because I mean, you would be able to just say, oh, take like a free generating set for your module, and I'm going to deduce it for an arbitrary module from the free case. Unfortunately, like Hilbert modules don't behave that nicely. So we heard last week people talk about like frames of Hilbert modules and bases, and I mean, basically the relationship between free Hilbert modules or representable Hilbert modules in this case and arbitrary ones is like a little tough, and you don't always have like an easy basis or like something that generates it. So basically, I mean, the real challenge in proving this theorem is that this is an equivalence of functors for all modules. Again, the fact that it's an isometry is kind of obvious once you work out what the definition is, but the fact that it's surjective for general modules, like that is the challenge. So David Blecher was thinking about this problem for C-star algebras in the 90s, and he proved a lemma that proved to be sort of the key between, like, of moving between like arbitrary modules and free modules. And I've like adapted that to the C-star category case, and it looks like this. This is, he didn't call this the approximate projectivity lemma. I've called it that. So basically, if you have a right Hilbert module, there's a set of operators which come from free modules and go into M, such that if you compose them with their adjoint, then so you have operators on M now. This converges not in the norm, but in the strong topology. So pointwise, this converges to the identity on M. So this is like the tool that we're going to use to move between the free case and the arbitrary case. I won't have time to like talk about the proof for this. It involves a bunch of things. There's a theorem of Brown's in there. There's a lemma of Lance's about, you know, compact relative versus like strong topologies. I'm not going to go into that right now because I won't have time. But yeah, you can prove this for C-star categories. Okay, so really quickly, how do we deduce the Eilenberg-Watts theorem from this lemma I just told you about? So, I mean, if you look back on this, we have these like operators, right? So we can just draw like a naturality diagram for this, like this transformation of functors psi that we just had. And we're going to do it for phi lambda and for phi lambda star both. So the goal here of this game is to prove that the top map is surjective, or that it has dense range, and then that's going to let us do the trick. So how do we do that? Well, this is a naturality diagram, so if you just restrict to the upward or the downward vertical arrows, like this commutes. The bottom map is an isomorphism because the bottom map, that's a free module. And because these functors have this like unitality and these continuity requirements, then these two nets in hill B are also going to converge to the identity, like we said before. So then really quickly, I mean, how do you do something like this? I mean, so we want to show that like an arbitrary element of f of m, and by the way, it's f of m of y, it's over some object of b, but I've just suppressed that, is like in the image of psi. How do you do that? Well, you know, you can approximate it using this strong continuity thing by things coming from this bottom right thing, and those things have to all come from the bottom left because the bottom map is an isomorphism, and then you can push those back up to there and sort of mess around and you can get to this one. This is the Eilenberg. This is the proof of the Eilenberg-Watts theorem over C-star categories. Really quickly. I don't have tons of time, so I'm just going to really quickly. Yeah. So this is surjective certain equivalence in all modules. Really quickly, like a next question to ask about this is like, okay, so now we've described these functors of Hilbert module categories as being given by bimodules. So which bimodules give us like equivalences? Which bimodules give us Morita equivalences of C-star categories? And I have a proof for that in my thesis, which basically says that the following things are equal. This goes back to, well, Echterhoff I think is a good reference for like what I'm about to say, and one of these three equivalences is also in this thesis that I just mentioned at the start. So you can say tensoring with E gives you an equivalence of categories. The other thing you could say is E is like a faithful functor onto the compact operators between the modules in its image, and it's also has this like ordered property that the inner products of like the E modules given by E are dense in B. And the final thing that you can say, which is maybe the most familiar to people who've looked at Morita equivalence of C-star algebras before, is that you have not just a B-valued product, but also an A-valued product that satisfies this imprimitivity sort of equation, and it lands in A, and then you just need both products to be full. That's cool. Okay, I have another slide of like things I'd like to do, like think about next. Do you think I should do that, or should we? Yeah. Okay. Cool. So, what are like the questions raised by this? I've got a year left on my PhD. Like, what am I going to think about for the rest of the year? So these are like some of the things I'm like interested in thinking about next. So, I mean, this Morita theorem that we had on the last slide, this allows you to really easily show that every C-star category is Morita equivalent to some C-star algebra. How do you do that really quickly? Well, you just pick like a B module which is full in B, and then you let the C-star algebra be like the compact operators on that B module. So that is going to give you, by the second characterization, it's going to give you a C-star algebra which is Morita equivalent to your arbitrarily chosen C-star category. So this means that the correspondence by category of C-star algebras is bi-equivalent to the correspondence by category of C-star categories. For people who haven't seen that before, it's just the bi-category that's given by, 0 cells are algebras or categories in this case, 1 cells are bimodules, 2 cells are like maps between bimodules. So this is like an alternative characterization of that, because now you can say, oh, my objects are just C-star categories. So a question that you might ask about this, to which I don't know the answer, is like, does this like simplify the study of that correspondence by category? And you can you can apply similar reasoning to like other like homotopical structures that people have put on C-star algebras recently. So now that you know that there's this like Morita equivalence with a C-star category, like does this study of any of these categories like simplify if we allow the objects to be categories? Sometimes when you allow for more objects, that means that you can do more things. So that's possible. Second thing is, so we know, can we build, I mean, this is really inspired by a project of my supervisor, Ivo Dell'Ambrogio, from 2012, where he built, I think one of the papers is also joined with Gonçalo Taboada, where he built a Morita homotopy theory of unital C-star categories. So, I mean, now that we know exactly what a Morita equivalence between non-unital C-star categories looks like, what might, can we build like some sort of Morita homotopy theory of non-unital C-star categories? Now we have this characterization. And then the final thing, which is a bit conceptual, is like, I mean, you can think of all of these sorts of Eilenberg-Watts theorems as basically telling you, like, the category of modules over this object is in some sense like the closure of this object, right? So finally generated projective modules, what is that? Well, it's the closure under like direct summons and direct sums of the ring. So, I mean, there's this kind of unwieldy lemma of Fletcher's which gives you this like net of operators that pass through this finite dimensional or finite rank module. But I mean, you could sort of ask, like, how do we like sort of categorify this? Like, what sort of colimit is that? And can we say like Hilbert is the closure of A under like this new type of colimit construction? Okay, that's where I'll end. Sorry for running over. Thank you so much.